Now let's look at another example. Which is fractions. Okay, so if we have our data representation, positional data representation with a point, we can approximate a lot of number with great precision, but we cannot represent something completely precisely if the fraction's denominator has factors other than 2 in binary. This is the same thing as our decimal representation system, where 1/7 cannot be accurately represented with a finite number of digits without using any symbol to represent repetition, that is. So that's something we can support with class, to support a different type of class called fraction, where we explicitly track the numerator and the denominator, and everything will be fine. But we can actually do this without object-oriented programming, without defining class. We simply do it with good old functions, which is shown here. Suppose I have a function called add fractions, and I take 2 representation of that. How do I represent that? If I don't have a class that defines multiple field, well, I can use tuple. So a fraction of 1/2 would be indicated like this, 1, 2. So then when we're adding 2 fractions, we will use a0, because we know that's the numerator of the first fraction, and a1 is the denominator. Okay, so we can do this. And if we want to print this in somewhat of a fancier format, rather than just print it as a tuple, we can do the same thing by defining a function. This is sort of similar to the string operator that we overloaded in the class design. So you can get the job done. And you can run this, it will work. And let's say you want bells and whistles. Let's say we want to simplify a fraction. If it's 2/4, we want to make it 1/2, and we can do that. We can define a function called simplify. And to simplify a fraction is really easy. We have to divide the fraction's numerator and denominator by the greatest common divisor. So G has to be the GCD from the 2 numbers. Okay, you can write your own code to do GCD. You can use built-in library calls to do that. Here's one example to do that from scratch. I believe this is correct. And you can do that, and then you can use it as such. You define a fraction as a tuple, again, another fraction, and you can add them together with a function call like that. If you don't like the result or want to make sure the result is simplified, you call that on the resulting tuple, and you get a new tuple. You can print it. When you do that, it's going to be printed like a fraction. So in this case, I guess that's 1/2 over 3/4, but plus 3/4, that would be 5/4. So you get a printout that looks like that, right? And if you don't like it, you can invoke the function to make it a string, and it will print out as such. So you can do all of that seems to come with class definition, that you allow a new data type to be created, and you can even overwrite the operators, stuff like that. So really, this is not that different. It may look better. Here's the class definition, the class-based version of it. We would be defining a class called fraction. Okay, and we would call the numerator, instead of the 0th element in a tuple and the first element to represent the denominator, we give them names. Okay, the .n is the numerator, dot d is the denominator, and we have an initializer or constructor. We define a function called GCD over here so that we can use it to simplify. And the simplify is very simple, very similar to the example early on, except now we're operating on the object itself. So we're just doing in-place changes rather than creating a new object, as was the case early on. And to show add, we overload the operator. Remember, that's the way to operate, to overload the operator this, and another operator to define how to print this into string. You can imagine this is not shown, it's too wide, it's cut off, but you know what is happening. So now, instead of a tuple, we would say this is of class fraction, and it has two parameters that we initialize in the constructor, and now we can do add, simplify would look like this, and then we can print it out, and you will see that it all works. It looks pretty normal and similar to what we did before. So both approaches can get the job done. So that really isn't what OOP is for. I mean, this is one way to make it perhaps a little bit cleaner, but really the benefit of OOP comes from all these other cool things that we can do, which we will discuss next week. Okay? So here is a brief preview of that. This is a rather simple thing. Since we overloaded the function add, can we overload operator add plus sign? What is this? You can probably guess that's greater than. If you don't, that's fine. But this is really what it is. It's greater than. So we're defining the operator greater than to be simply, this is not, I guess, exactly correct, because this is just a simple way using, I'm calculating, I'm approximating the fraction. So this is not precise, but for simplicity, I did that. If A, the value is B, is bigger than B, then we say it's greater than. So now look what you can do. We can do all these things that we did before, obviously, because we didn't change anything. We just added something. And we had a list over here. And in the class, I tried this with, if we have tuples. So if you have a list that looks something like that, right? It's a tuple. It's a list of tuples. So 1, 2, perhaps 3, 4, and whatnot. If you have a list like that, and you try to take the maximum element of the list, see what happens. It's very weird, okay? Because the maximum element is the element inside that list that is bigger than everything else. Now, how does this compare to that in terms of magnitude? What does that even mean? For us, it's clear, because now we're using fractions. In the example, we're using tuple to represent fraction, so we know the meaning of this is 3/4, but the computer doesn't. Who knows what maybe this is the position. Maybe this is the XY coordinate of a pixel on the screen, right? And by defining the operator over here in the class version, without us writing a code to find the maximum element, this would actually work. Now, this is called polymorphism, and we will kind of discuss a little bit. It's a complicated subject that I don't think we have enough time to delve on, but this is really what is happening. By redefining or overloading the operator, then a lot of functionality that depends on the building block of this operator is automatically already implemented. Okay, so in other words, the max procedure is simply some sort of a procedure to find the relationship between two elements. Okay, a collection of these pair elements, what it really does is it goes through the list and take the first element, compare it to the second. If it's bigger, remember the second, and so on. And at the end of this list, we'll find the maximum element. And this whole code was written using greater than. You can try this. If you define less than, it doesn't work. At least I tried it, it didn't work. It means this particular implementation was using greater than, always comparing. If it's greater than, then remember this. Okay, and this is called polymorphism, and we'll explain that in more detail. Here, I just want to note that just defining the class in itself is not necessarily more superior. If it's just now we can call fraction, that is a little bit prettier perhaps, but not a big deal. The big deal is what this enables you, not the class definition itself is a big deal, but what it enables. It enables, we will see, composition, which is perhaps the smallest benefit, but the next one, inheritance, that gives you a big deal, polymorphism, and these are the subject for the next class. So for now, note that we can start to define classes. We can use all these collection variables inside the class. So your member variable, we had simplistic member variables, numerator, denominator. We can have more sophisticated one. We can have a dictionary here, a tuple there. This could be your class, and every object that you create can be part of something else. It can be an element inside a list, a dictionary, and you can nest arbitrarily. So you can take your own implementation, you can go to the standard library, or some new module other people are sharing on the internet, so you can use them. So this is how we're creating complex system, by having these smaller building blocks that you didn't have to build always from scratch. You can use them and build bigger system, build more sophisticated system that does things that you want to do. You're really only limited by your knowledge of what exists and your creativity. So the data structure can be so complex, and it can do a lot of things for you. And obviously, that requires practice, experience. It's not what we want to accomplish in 6 weeks. We just want to give you perhaps a first look at these tools and what you need to do in order to code in later courses. So to summarize, what we talked about in this week, first we understood scope. Okay? In general, how that works, you have a function, the variable defined inside that function is only used locally inside that function. So you give a lot of names to different objects or different variables. These names sometimes refer to this, sometimes refer to that. This notion is called binding, and when a name is bound to an object depends on where you are, where it was defined, and all that. So we saw earlier in the example, we defined string A outside the function, and inside the function it was rebound to something else. It was bound to a different string A, the local string A. Largely this is just, the simple rule, which is not always true. Inside the function you can consider that as a completely isolated reality from what comes outside. And this also applies to class as well. You have a class that you can define objects. I'd like to sort of make an analogy that this class that you're defining is like a template, like a cookie cutter, and they're not real. They're there. They're not real in the sense it's not a real object. It's a blueprint, a template to create an object, and the real objects are created while using the name of the class. When you say A equal fraction something, you're creating an object A is now an object of class fraction. And so this is the building block to allow us to do next week inheritance, polymorphism, and also composition.